the fifth part of this lecture for section 2.3. As I was saying, this is the same type of problem as we just looked at. The difference is that it's a little more abstract, and we are now given the function 4 divided by x that we are to use with this. In order to think about this problem and to begin to write it, the limit as delta x approaches 0, I can pretty easily get everything that I need in here, delta x and all that, but I need to think about what does it mean to have f of x plus delta x. And all I need to remind you of is this quantity in here is all of the input expression, which means that f of x plus delta x is the same thing as 4 divided by, and everywhere I see the input variable in the function, I'm going to replace it with the input expression x plus delta x. So I have 4 divided by x plus delta x minus f of x, which is 4 divided by x. Okay. In order to continue working on this problem, I'm going to have to consider the numerator and write that as one fraction, and then consider that the denominator is also a fraction divided by 1. So I have delta x divided by 1. So let's work on the numerator and get that into one fraction. So the limit as delta x approaches 0, and we have down here our delta x divided by 1, okay? But in the numerator up here, I've got two fractions. They do not have the same denominator. I need to choose a common denominator. Common denominator is going to be x, the quantity x plus delta x. And in the first fraction, what do I need to multiply with this denominator to make it look like this? And that would be x divided by x, and so this would be 4x divided by x plus delta x minus, okay, and so I need to have my common denominator on this fraction as well. And I have 4. Well, what do I need to multiply this denominator with in order to have the common denominator? And that would be the quantity x plus delta x. Okay. So I now have the limit as delta x approaches 0 of, I now have common denominators up here. I'm now ready to combine the numerators, so I have 4x minus, now be real careful, this is a subtraction. If I multiply 4 times x, I get 4x, but I'm going to have minus 4x, and I have 4 times delta x, but I have a subtraction out there, so it's minus 4 delta x, all of that divided by x, the quantity x plus delta x, and that's divided by delta x divided by 1. Okay. Well, we went over this, I believe, that if we're going to divide by a fraction, we need to invert and multiply. So we're going to have the limit as delta x approaches 0. Now, while we do this next rewrite, we can also consider that up here these terms are going to cancel. So I will do that, and I end up with negative 4 delta x divided by x times x plus delta x times, and we're going to invert this and multiply 1 divided by delta x. Now, if it helps, we'll put brackets around that to remind us that this is all the function expression that we're going to be taking the limit of. As we do that, notice that our delta x factors are going to cancel. And we end up then with negative 4 divided by x, the quantity x plus delta x. Now let's go back to the top and look at this. We had to do all of this work because we're taking delta x to 0. In the original problem, we had delta x in our denominator that was preventing us from using direct substitution. We need to get that to a point where we no longer have that factor of delta x in the denominator, and at this point in the problem, that has happened. Once we have that factor out of the way, now remember, this is not a factor of the entire denominator, so it does not cause us any trouble. It's the factor of that was causing us trouble. So at this point, is it proper, is it permissible to substitute 0 in? And the answer is yes. Notice I do not write the limit anymore because I am now using direct substitution. And my answer would be -4 divided by x squared. We can check that on the Inspire. I think we've done enough of that. You can go back and review how that was done, but let's move on. We have a problem now. This is the last problem of our set 2.3. And we're going to use something which is called the position function. We're going to see that coming up other times in our work. It is the function we use to determine the position of an object, one that's being either shot into the air or dropped from a height of something. So this gives the height, this function gives the height in feet of an object that has fallen for t seconds, so that's one of our variables, from a height, in this case, of 1,000 feet. So we're being very specific that it is 1,000 feet. Later on we'll have problems where we would change that. The velocity at time t equals a seconds is given by this. Now we're going to talk more about how velocity compares to position function, but for those of you who have not had this before, don't worry about that relationship. Instead, we're focusing on the fact that we have a limit as t approaches a. So t is the seconds from a height, and we're going to evaluate that as it approaches a given number of seconds. And we have S of A. S of A would be the time we're approaching minus S of t divided by A minus t. Okay, so using that formula, if a construction worker drops a wrench from a height of 1,000 feet, how fast will the wrench be falling? Remember, this is going to give us the velocity. So this formula is giving us the velocity. So the velocity in terms of t is given by the limit as t approaches a of S of A minus S of t divided by A minus t. Okay, our problem is asking then for v of 5, because we're going to look at this 5 seconds after it has dropped. So we have the limit as t approaches 5, and this would be then S of 5 minus S of t divided by 5 minus t. That's the limit as t approaches 5. And if we put 5 into this, we're going to have negative 16 times 5 squared plus 1,000 minus negative 16t squared plus 1,000, all of that divided by 5 minus t. If we look at this, we would have the limit as t approaches 5, and I'm going to simplify this to negative 16 25 plus t squared divided by 5 minus t. You can go through and do the calculations there. This would be the limit as t approaches 5, negative 16, and we can factor this as 5 plus t and 5 minus t divided by 5 minus t. Why couldn't we use direct substitution? Again, the reason because it would make the denominator equal to 0. Once I have this taken care of, I can then factor or cancel those factors out. The problem is gone, and I now am able to go back and use direct substitution on this, and my answer would turn out to be negative 160 feet per second. Okay, the last problem is one that we will see if we have time to do. We'll get as far as we can, and if not, we'll come back and do this in class. This problem is asking at what velocity will the wrench impact the ground, at what velocity will the wrench impact the ground. So we're looking at S of t equaling 0, because when it hits the ground, the distance above ground is 0, and that's negative 16t squared plus 1,000. If we solve this, we'd end up with, let's see, first we'd have t squared is negative 1,000 divided by negative 16. We're going to end up with 5/2 the square root of 10 seconds. We want to know then what is the velocity at 5/2 the square root of 10 seconds. We found out that we need to look at the limit then as t approaches this 5 square root 10 divided by 2, and this would then be s of 5 square root 10 divided by 2 minus s of t divided by 5/2 square root 10 minus t. We're running out of time on this session, and I don't want to go to another session, so I'm just going to say dot, dot, dot. You can finish in. It's negative 253 feet per second would be this value. This, by the way, is approximately 7.9 seconds if you're interested. Okay, well, this concludes our lesson. We'll come back. I'll see you on Tuesday. Please go back and review this. You can go in as slow as you wish and capture as much as you can, understanding not only the content, most importantly the content, but also the working of the Inspire. So have a nice weekend, and I will see you on Tuesday.